Hello everyone, this is Group 6 with Sean Slay, Skylar Johnson, Michelle Reed, and myself, Ryan Copeland. I'm going to start off the video of talking briefly about Module 1, which mainly consisted of reintroducing us to American history, starting with Columbus sailing the ocean blue in 1492, to the American Revolution, to our greatest engineering achievement of the time, the Erie Canal. The module goes on to talk about the amount of people that were in America around the time that we started talking about the class, which is about 5 million people, including about 1 million slaves, which were meant for working on the southern plantations, which were known to be the biggest farms around, which is what all of the Americas were basically, was just a huge farm town at this point in time. They never really got big into engineering quite yet. But the module then starts talking about how France and Britain influenced the American nation to get into engineering. The French they were more promoting a military style of engineering background where the government would pay for your schooling, education, and teach you how to do everything, when in return you would basically be working for them, building up their military, their buildings, all that sort of stuff. The British trained people on the job because they thought a how it works style is better than why it works. They didn't want people to tell them why it worked or how to do it. They wanted people to be able to build things the entire time, like engineer themselves into a better community. And the social classes were a little different. The French engineers came from a higher social class, an upper middle class, whereas the British came from a lower middle class, which would consisting of working class or trade backgrounds, which is what highly influenced their engineering.
Hello class, my name is Skylar Johnson. I'm going to be going over the Module 2 of History of Engineering. Module 2 is an outline of how organized and established engineering came to be in the United States. The highlights to remember would be how and why professional engineering societies came to be. The 4 major engineering societies that we came across in this module were the ASME, the AIEE, the ASCE, and the AIME, which were created to set a standard and criteria for engineers within a society as a whole. Basically, not everyone could formally call themselves an engineer without the proper criteria being met within the societies. During this module, the way engineers were educated changed more and more from the British style to the French style, and where formal engineering education was established. The Morrill Land Grant was a pivotal event in the establishment of formal engineering education. It allowed the creation of universities and colleges across the nation. Land granted to the states was sold, and the proceeds were used to build and staff universities, which offered many different degrees, including formal engineering education. Another large event that was becoming more and more well known was the availability of engineering jobs and education for women and African Americans. It came to light in Module 2 here, where more often than not, the women who desired to enter the engineering fields were unable to do so even after the women's suffrage movement. The same went for African Americans after the Civil War and the abolishment of slavery. Those hindrances were overcome over time, but placed a huge deterrent to those brilliant minds within those fields.
Hey class, my name is Sean Slay, and I will be discussing patterns of inventions, independent inventors, and industrial research labs that we found in Module 3. For patterns of inventions, we see radical invention, conservative inventions, and discuss the linear model. Radical invention introduces new ways of doing things and can hurt established industries. For example, with the creation of electric light, the gas industry would eventually suffer. In conservative invention, this refines existing industries, and this can be something like using better materials for the light bulbs. The linear model suggests basic research leads to technological innovation. Money comes in, research is done, development happens, new technology spawns, and it improves society. However, many innovations are created through tinkering. The 1966 Hindsight study analyzed $10 billion that were spent in research funding. It showed that only 9% of improvements came from science and the rest was from technology. The linear model is a flawed explanation of the innovation process that overlooks tinkering and many other ways of innovation. Independent inventors, such as Edison, Tesla, and the Wright brothers, were a large part of our technology improvements as we entered the 20th century. Many independent inventors focused on radical inventions. Most independent inventors grew up in rural areas and had little formal education, but showed high mechanical aptitude. Professional inventors had to rely on investors to constantly invent, where the non-professional inventors usually held day jobs and invented in their spare time, and typically this was spent on one project. In industrial research labs, this changed the corporate culture of engineering in America, where you previously had independent inventors who occasionally worked with a small team. Industrial research labs were much larger. The rise of these labs are linked to the increasing complexity of certain industries, as well as the growth of wealth and power in corporations. Many such labs focus on more conservative innovations to improve existing products. They had plenty of financial support, and in turn, they could afford large, diverse staffs. And around this time, this is when you start to hear less about the independent inventor because efforts of the lab were from a collective. An example of an industrial research lab can be seen with Bell Labs. There were multiple departments for research and development, patent control, and even facility upkeep. And with that, this concludes our presentation. Good luck, everyone.